All right, guys. So today we are going to learn a little bit more about voltaic cells. We're going to learn how to notate them. There's a shorthand which makes it a lot easier. And we're going to practice also figuring out, given two standard reductions of the different half cells, which one actually becomes oxidized and which one is the one that stays reduced so that we can create the spontaneous or a voltaic, or there's even a third word, galvanic cell. So galvanic cells, spontaneous cells, and voltaic cells all mean the same thing. Their overall voltage has to be positive. Okay, so here we go. We have a few more that we're going to practice this with. We're also going to use this to describe the cell notation. So I want to show you what we have in the cell notation. And let's write this pretty big. So, for example, this one that we just did last time, we had iodine and iron, and we also realized that, okay, if we did iodine, we had a positive 0.5355 volts, and if we did iron, we had a negative 0.447 volts. One of them we had to flip because these were both standard reductions. So we flipped the iron. So we used this. We used iron solid going to iron plus 2, and that gave us a positive 0.447 volts. So we added it together, we had a positive 0.983 volts. Okay, voltages to be spontaneous have to be positive. So if we want spontaneous cells, we have to have positive voltages. Okay? Now, the other thing that we have to do we really want to write out all this mess every single time we write out a cell? No. So here's the shorthand how to do this. So we use the oxidized side. And the oxidized, remember, an-ox. So we could actually call this the anode side as well. We started with iron, and we ended with iron plus 2. So this is our reactant, and this is our product on the anode side. And then we put in a double line. This signifies the salt bridge that separates, I can't spell bridge, that separates the half cells from each other. And then on the other side of the salt bridge, we put in what is reduced, the reduction side. So we put in the cathode side. Okay, remember red cathode side. So we start with our reactants, which is iodine. And then we do a slash, and then we put in our products, which is the iodide ion. Okay, so on the left-hand side for cell notation, we always put the anode. What is oxidized? Okay, we put the reactants first, put a slash, and then put the products. Then we put in our double line, which means the salt bridge. And then on the right side of the salt bridge, we put the cathode or the reduction reaction. We put our reactants first, a slash, and then we put our product. And that is the shorthand notation for all of this up here. Okay, makes it a lot easier, doesn't it? Okay, so let's practice on a couple of these. And this is, once again, not in your notes this year, but this is the way that we do this, okay? So we put the anode side on the left, the cathode side on the right, and we put in our reactants and our products. Okay, so example 3. For each of these pairs of half reactions, we're going to write the balanced equation for the overall cell reaction. So we have to balance electrons here, and we have to calculate the standard potential. Okay? So we're going to describe the reaction using cell notation. So the first thing we've got to do is we have got to look up these cell potentials. So platinum plus two electrons going to platinum solid is positive 1.18. And I'm using the sheet from I'm using the table from a couple pages ago. So if you want to refer to that, or it's on page, I think, 68 of your workbook, there's another table in the homework section as well. And then if I look up tin plus two electrons going to solid tin, I get a voltage of negative 0.138 volts. Okay? Now notice these are both reduction. So I need to have one of these be oxidized. So we always flip the one that has the lowest value, which would be tin. This is negative 0.138 is less than 1.18 volts, right? So we're going to flip that one. So we're actually going to have tin solid going to tin plus two electrons, and that will give us a positive 0.138 volts. Okay? Now notice we have the same amount of electrons coming and going, 2 and 2. So when we match this equation, let's change this equation with this equation, don't these electrons, they're on opposite sides of the equation, or the reaction arrow, so they basically cancel out. So our overall equation will be, we always start with the anode, the oxidized. So we're going to have tin plus platinum plus 2 going to tin plus 2 and platinum solid. Okay, so that would be our overall reaction. And then for the voltage, we just have to add both of these together. So when we add both of those together, and we can only go to the hundredth spot, so this would give us a voltage of 1.32 volts total on that cell. Not a huge amount of energy, but it would give us some. Okay, so let's do this next one. We've got cobalt plus 2 electrons going to cobalt solid, and we've got chromium 3 plus 3 electrons going to chromium solid. First thing we've got to do is we have got to look up these cell potentials. So if I go to the sheet the table a couple pages ago, chromium is a negative 0.28 volts right here. Or sorry, not chromium, cobalt is a negative 0.28 volts. And chromium is a negative 0.74 volts. Okay? So which one has the lower value? Chromium does. So we are going to flip chromium. We are going to make that the oxidized. So we are actually going to have chromium going to chromium plus 3 electrons. Now let's look at our electrons. Now if I look at my electrons, I've got 2 here and I've got 3 here. So what's my least common multiple between 2 and 3? It's 6. So that means I'm going to have to multiply everything in the cobalt by 3, and I'm going to have to multiply everything in the chrome by 2 to get 6 electrons coming and going. Okay? So that means I'm going to have 2 chromes plus 3 cobalt plus 2s going to 2 chrome plus 3s and 3 cobalt solids. Okay? So when we flip this, this will give us a positive 0.74 volts. And we add those two together, we get an overall voltage. So we're going to add this and this together. That will give us an overall voltage of 0.46 volts on that cell. Oh, you know what I forgot to do? I forgot to do the cell notation. So let's do the cell notation really quick for B because we're in that mindset. Okay, so we are going to start with our oxidized, which is our chrome. So our reactant was chrome. We ended up with chrome plus 3. Then we have our salt bridge. And then on our reduction, we started with cobalt plus 2 and we ended up with cobalt solid. Okay, so that would be the cell notation for this chrome. Okay, let's do the cell notation. Let's go back up to the tin and the platinum one. Let me change my color really quick. So our oxidized, or our anode, started with tin. We ended up with tin plus 2. Then our salt bridge. Then our reduced, we started with platinum plus 2, and we ended up with platinum solid. So this would be our cell notation for the tin and platinum cell that we created in our first example. Okay, now I think I'm back on track. Okay, so let's look at mercury. We have mercury plus 2, and we have that cell potential as 0.85 volts. Okay, and then chrome plus 2, instead of chrome 3, we have this potential as 0.913 volts. And they're both positive. So when we do this, we are going to, let's see, am I looking at this correctly? Let me check this really quick. So mercury plus 2. Nope, that is not what this says. Okay, let me erase this really quick. Mercury plus 2, maybe mercury plus 2, yep. This is plus 0.85. Okay, and then chrome plus 2. Okay, this is a negative. This is what was messing me up. This is indeed a negative. So this chrome is less than the value for the hydrogen, so this is the one we are going to flip. So we are going to have chrome solid going to chrome plus 2 electrons. And that will give us a positive 0.913 volts. Okay, so once again, let's look at our electrons. We've got 2 electrons here and we've got 2 electrons here. So they actually cancel out quite nicely. So when we put both of these equations together, we will have chrome plus mercury plus 2 going to chrome plus 2 and mercury. Okay, so that will be our overall notation, or our overall reaction. So the overall voltage for this, we're going to add these two together. So when we add these two together, we will get a positive 1.76 volts. Okay, our cell notation, we're going to start with the oxidized, or the anode. So we start with chrome. We end up with chrome plus 2. our salt bridge, and then our cathode, or the reduced thing, we started with mercury plus 2, and we end up with mercury. Okay? So that would be our cell notation right here. All right. Write a balanced chemical equation for the standard cell notations listed below. So let's look at this. If I start with iodine, negative, and I go to iodine, I am losing electrons here, right? And I definitely need to put in 2 iodides to make the I2, right? I've got to have the same amount of atoms of iodine. So 2 iodides, I negatives, going to iodine, I2, plus 2 electrons. Do you agree with what's going on there? Okay, and then how do I go from an iron 3 to an iron 2? I have to add an electron, right? So iron plus 3 plus an electron will get me iron plus 2. Now the thing is, we've got 1 electron here and we've got 2. So that means I'm going to need to double my irons. Okay? So if I double my iron, overall, I'm going to start off with 2 iodides plus 2 iron plus 3s. My electrons will cancel because I've got 2 of them. And then I will have iodine and 2 iron plus 2s. Okay? Now, if I want to figure out the cell potential here, I could also look that up. So iodine cell potential here is a negative 0.5363, and iron cell potential here is a positive 0.771 volts. So if I add this all together, I get a positive 0.235 volts. Okay, so that cell is spontaneous. All right, let's look at this. So we've got tin. So how do I go from solid tin to tin plus 2? I have to have 2 electrons with this, don't I? And if I go from silver plus 1 plus an electron will get me to silver, right? So I'm going to need to double my silvers here in order to get that to go. Okay, so I will have tin plus 2 silvers plus 1's going to 2 silvers plus tin plus 2, because my electrons will cancel out. Okay, now let's put on our voltages here. So if I had my voltages here, I would have 0.138 volts for my tin, and my silver is 0.800 volts. So when we add this together, we get a total voltage of 0.938 volts. So that is a spontaneous reaction. Okay, last but not least, zinc. How do I go from zinc to zinc plus 2 with electrons? I need 2 electrons here. So electrons are lost, so zinc's oxidized. And cadmium plus 2 electrons will give me cadmium solid. Okay, so I have 2 electrons coming and going. So these electrons cancel. I add these up. I get, this is zinc, cadmium plus 2. So I have zinc plus cadmium plus 2 will give me zinc plus 2 plus cadmium. Okay, notice that on these equations, once I balance them, the charges on both sides of the equation should be the same. I have +2 on both sides of the equation. Okay, so if I wanted to look at the value of this cell, zinc is a positive 0.762 volts, and cadmium here is a negative 0.403 volts, the way we have it written. So overall, we get a 0.359 volts. Still positive, so it is still spontaneous. Okay, so this is how we use cell notation. This is how we use the voltages from our standard table. And you can check my standard table voltages off of the standard table that you have in your workbook. Okay, and how we balance. Remember, the electrons coming and going have to be the same. So now you know how to use the notation. You know how to use the voltages to get the standard potential of the cell and to balance the total chemical equation. So please let me know if you have any questions. We'll talk to you later. See ya. Bye.